Well, we practice image filter implementations on an FPGA. So we want to apply steerable filters on a FPGA embedded hardware. And I'm Zach Simmons. This is Remy Schott. This is Alvaro Varela. So in this presentation, we're going to talk about our objectives in this project, like where we were in May, where we wanted to go, a background about steerable filters and FPGAs themselves, talk about a MATLAB implementation we did to check our work, a multi-window partial buffer filtering algorithm, which looked very promising on FPGA, but we ended up just implementing it in MATLAB with the time allotted, describe how convolution works in VHDL, talk about our steerable implementations in VHDL and have some example images, talk about the research utilization and the time required to filter the images, and how we're going to continue our work. So our main objectives were to implement image filters on low-level hardware, field programmable gate arrays. And we wanted to properly utilize the parallel processing of FPGAs, and we did that through things like pipelining and different types of memory management. We used the properties of filters themselves, like separability, to save on computation costs, and overall we're expanding on the limited work done on FPGAs, because it's a fairly new field. So convolution is an operation between two mathematical functions. And here I'm describing the discrete convolution of an image with a mask. And that's one-dimensional. No, it's two-dimensional of an image with a mask. And it's the filtered pixel at P and Q in the image. 2D convolution is very high computational cost, requiring with an M by N image and an S by R mask, M times S times N times R multiplications, and M times N times S times R minus 1 additions. So we try to overcome that by applying 1D convolutions multiple times, and with the FPGA we can actually pipeline them to save computation costs and time. So the main filter we're using is Gaussian filters, and it's described by the following equation, where sigma is the standard deviation of the Gaussian blur. And since the 2D Gaussian filter, the function can be described by both its 1D functions with respect to x and y, and multiplied together they'll yield that 2D function. So we can apply the filters in orthogonal directions to yield the 2D filter. So instead of applying a 2D filter mask, we can apply two 1D vectors. So the two main papers that we based a lot of our research on, I mean, there was a lot more in the literature search, were the design and use of steerable filters by Freeman and Allison. And it's the first paper to really introduce steerability in filters. And it's breaking up directional filters into linear separable basis filters that you can apply at multiple angles. And actually presents a theorem for finding the steering angles for these basis filters. And also the paper Efficient Directional Gaussian Smoothers by Dr. Halimpides. And it describes the value of smoothing an image before processing. We can use it to take care of noise, missing data. And actually what it accomplishes is it averages around pixels around certain pixels and introduces a thing called decimation factor, which can then take advantage of that to then skip pixels in the later steerable implementation. Because the pixels in that region are so similar, it doesn't matter how they're filtered. And you gain much more smoothing with a similar sigma than something else. Steerable filters, they allow for that oriented edge detections, and it's often hand in hand with separability because they're based on directional smoothing filters. And a steerable filter, you can apply this filter in multiple angles to yield that. We're using steerable Gaussian filters, and as I said before, we must first smooth the Gaussian filter, and then we have a steerable filter that we can use the decimation factor on and apply it multiple directions. So to introduce FPGAs, they're known as field programmable gate arrays, and they're integrated circuits, they're embedded hardware. And they're kind of building upon something called like an ASIC, which is an application-specific integrated circuit. And what FPGAs allow you to do is reprogram them, experiment on them, and as the algorithm develops, you can keep reflashing your FPGA. And what they're actually made out of is logic blocks with our FPGAs, most of them are four input lookup tables and a flip-flop for memory for that, and also block RAM, which is RAM in the actual chip. And when you program it, and what we use is Xilinx, which software that's for the FPGAs. And it will program and route these logic blocks to accomplish our embedded hardware. And they have a lot more flexibility than ASICs because we're allowed to reprogram them. So here are the results images from the MATLAB implementation. It's a 128 by 128 image, so it's blown up here to see better, but you can see it's very pixelated. It's the original Lena image in grayscale. And it's very smooth with the Gaussian blur of sigma equals 2 vertically. You can see here we have zero padding left over that's going to get taken care of after the horizontal convolution. Now we can see a full horizontally and vertically smoothed image with this sigma 2. So then we applied a steerable filter in the vertical direction with sigma equals 2 radical 3, and we got that from a formula we'll see later where we use a sigma y of 4 and a sigma x of 2 in the formula square root of sigma y squared minus sigma x squared. And then in the horizontal direction with sigma equals square root of 3, and these aren't built upon each other, they're done separately, so you see there's zero padding left in this too. But then with a diagonal direction and a decimation factor of 2, I mean, this is really the goal image we had. And you can see it's kind of blurred beyond recognition here, and that's because we are using a large filter on a smaller image. We just did that to keep in line with what we're doing in VHDL for how much resources we have on the Spartan 3 platform. And I talked before about how there was a multi-window partial buffering scheme that we've read literature on it, and I implemented it in MATLAB, but this is really just a take on methods they were talking about. It's not the exact methods in the paper. If we had time, we would have implemented the exact methods in the paper on FPGAs, but really we just used that for a resource comparison and speed comparison, because that's exactly what this paper was. We weren't implementing an image filtering algorithm on FPGAs for the first time, but taking an algorithm for FPGAs and re-implementing it. So here we can see the filter mask we're using in this example and a zero padded image, which is the full zero pad in the horizontal and vertical directions is the x length or y length minus 1. So you can see we have 2 zeros horizontally and 2 zeros vertically with a 3x3 mask. And really this is just showing what convolution actually would be in 2D convolution. We have our window from the image, and then standard 2D filtering piecewise multiplies these together and adds them to yield the first pixel value of 103. And the way I designed this is we have 3 things in memory the size of the image mask. We have the image window, and then the filtered values, each of these rows correspond to a column in the filter mask. And this is this column applied to that filter, added together, and so on. So then we can take that diagonal, and the sum of that diagonal is a filtered pixel. So then to move this window, we just move all these values in the image window and the filtered values and keep the ones left over. And that allows us to save some time, but we have wasted pixels in this lower triangular. So it's not a perfect algorithm, but it allows for some parallelizability in the future. And it also has the issue of when you go to a next row, it is cleared out. There are different ways memory could be managed, but it gets the main idea of this paper where you're taking a 2D filter that may or may not have the ability to be separable by basis functions, because not every filter can be, and you're just applying the vectors piecewise and then putting them back together.
I'm going to discuss convolution in VHDL. Basically what you do to convolve an image, you use MATLAB to get your pixel values. You read your image into MATLAB and then you zero pad it. Got it?
Yeah.
Okay. Which one's the laser pointer?
Oh,
The top, okay. So also in MATLAB, you zero pad your image. Basically what you'll see here is, say, for example, this is the top of your image. I use 3 pixels border on my image. This would have 3 pixels all around to compensate for the size of your mask. I'm using a 1x7 mask, and you want the center of your mask to go on the edge of the image. And we use the border, the zero padded border, to compensate for that. Next step would be to write a controller that returns your pixel values from your block RAM. For the vertical mask, what we do is we take the first pixel at the top left, and we're going to convolve with our mask, which will go vertically. It's a 1x7 mask. So I was using a 134 by 134 image. It was 128 by 128 zero padded with 3 pixels per side. So to get your pixel values, you return your first pixel value. The row increments by 134 to get you to your second pixel value, and you do that over and over. Once you get to the end of the first column, you increment your column and just do the same thing. Keep doing that till all our pixel values are read. Next, that goes to a module that takes the block RAM outputs, all our pixel values from the last step. This module also stores the mask values and outputs the pixel values and the mask values. So what you'll see over here, the top 7, those are our pixel values. Our mask values are stored down here. Those values are derived from the equations from the previous slides. Once the output comes out of that module, they get sent to a series of multipliers which are embedded in the FPGA, whose sole job is to multiply the values. Right here you'll see a schematic top module 1 down here. Top module 1, that's comprised of our block RAM and our controller. Here's our image mask controller with the top 7 pixel values from our image and our mask values. Those get sent to a series of multipliers which each give us a 16-bit output from that original 8-bit output from our previous module. All that gets sent to an adder, which gives us our vertical convolution results. It basically takes the most significant bits from our 16-bit output and takes the 8 most significant for our result. This is a test bench waveform done in VHDL. You can see the outputs from each step are mask values and see how they progressively go forward and go to our adder, essentially.
Yes.
One quick question regarding your previous slide. Are these schematics generated by the VHDL software?
Yeah, it's the Xilinx software that generates.
How do I look at the output and try to see if that corresponds to your design? I just don't have the general idea how you look at the actual schematic and see if that exactly implements what you want to do.
Basically, it'll output all our VHDL results, and you can write that to a file, and then you compare that to what we did in MATLAB to make sure the results are right.
Okay. Well, it's hard to really just see the schematic.
Yeah, it's a little hard. This top module here, it basically builds on top of each other. Like the top module here, that's our block RAM with our image and controller that outputs the image values, and it goes into this, multiplies. Here, this top module 2, that's comprised of what you saw on the previous slide. Everything in the previous slides in this top module 2, and it sends it to the adder.
And also, later in our presentation, we have flow diagrams of how this actually works. Not on schematics, taken back from schematics. Right there.
Yeah. So this is the flow chart showing how our steerable and our steerable implementation, our steerable pipeline implementation works. And the main takeaway from these is that every time an arrow moves back like that, it's a clock cycle. So essentially, you can see in this design, the pipeline, it keeps a constant flow until the very end. That's when another clock cycle comes. And what's beneficial about that is that it increases the execution time. This pipeline implementation does the convolution in roughly 1 pixel per clock cycle, whereas this one takes roughly 3. And the reason is that while this design will take results from one convolution and then use it for the next convolution in the same cycle, the non-pipeline implementation finishes the entire, for example, horizontal convolution, and it finishes the entire vertical, and then the entire steered. We used a 45 degree for this, but you can theoretically use as many as you want to create an isotropic filter. So when we do the diagonal filtering, this is for the non-pipelined implementations. In the pipeline, we're getting the pixels in the order that they're being convolved, but we have the benefit in the non-pipelined implementation of having the entire image we want to filter prior to filtering it. So what we do is instead of reading from the top down, we read the image in a diagonal way. And this is beneficial because the way that our module works, you populate it with pixels, and then when you get to the next row, you have to get enough pixels yet again to do the correct convolution, because the bandwidth of our BRAM is only 1 pixel per cycle. That could be fixed by using RAM and other things, but we decided to exploit it for our design. So as you can see, it reads this pixel and these 2 0 pads, and it's convolving this pixel. Then it gets to the next row, and it reads these 3 pixels to convolve this one. And then it gets to the next pixel, and it uses this one. And so that basically, while you're not getting good efficiency in that diagonal, as you get towards the biggest diagonal, you're gaining a lot more pixels per thing. And this is a comparison of reading from top to bottom versus diagonally. When reading top to bottom, you have a summation like this one, which can be expressed as this equation. Well, actually, when you're reading top to bottom, it's this one right here, m times s squared. So that's, if you're using a mask of 11 and an image of 100 by 100, that would be 11,000 reads, whereas this one would be significantly less because it's not a linear function times a quadratic. And here's how our pipeline works. This is the memory management and just the general flow of pixels. So you can see here, this is the first row of the image. And once you get to this pixel, the 7th pixel, you can convolve, which gets stored there. This is the last pixel. Then it allows this pixel right here to be convolved and stored in this next FIFO. This FIFO is the size of the mask times the width of the image. And basically, it takes these pixels on this row and convolves them and sends them to the next FIFO. Following that, there will be a shift. So the next row, which would be right here, is now in this position. And then it convolves the middle pixel and yet again sends it here. And that continues indefinitely in this fashion. And then it goes over to the next row and sends that pixel, that pixel, that pixel, that pixel, that pixel, etc. And once there's enough pixels, it would be over 1,000. Their latency is about 1,000. To get this pixel, you need to get 1,000 of these. So there's a timing difference that has to be accounted for to store it in the BRAM. But essentially, once it has enough pixels, it takes these diagonals and convolves them and stores them here. Then these pixels next to it are shifted over to the side, and then this last pixel comes from here, and then it convolves it and would store it as the next pixel, etc. And this allows you to use the results of your previous convolution in real time to create a near 1 pixel per cycle result. So now I'll show you the results from the FPGA. These were ran in the VHD, in the Xilinx simulation, written to a file, and then read through MATLAB and viewed. We compared the matrices to ensure that they were the same. So this is our original Lena image. This is it filtered with sigma equals 1. That's just a horizontal and vertical 2D filter. Now, and then this is the horizontal and vertical steered, which Alvaro took care of. As you can see, you still have certain features here that are diagonal, but you definitely get a lot better of a blur in these directions. And this is with the decimation factor of 3. As you can see, it's a lot blurrier, and that's the main takeaway of the decimation factor, is that although it uses slightly more resources for the same mask, you're getting a better blur for your resources. And now we have the diagonal steering with a sigma of square root of 3, which is using the equation sigma y squared minus sigma x squared and taking the square root of that. So we're basically using a y filter of 2 and an x filter of 1 on the diagonal. So it's slightly more filtered in the vertical direction than the horizontal. So here's the 2 square root of 3, which as you can tell is more blurry. And finally, with a decimation factor of 2, you get a lot more significant of a blur with similar resource usages, which you'll see here. So this is the execution time, and you can see pipelining has a very significant effect. It's about 2 times faster in this case. It's about 3 times faster in this case, and yet again about 3 times faster in this case. So when we pipeline, we're speeding up our design significantly. But the downside is that the resources greatly increase with pipelining. But it's not as evident in these ones, but as you get to needing bigger masks or FIFOs to store the data, you can see that's like a 4 times increase in resources for the pipelined implementation. And additionally, in the pipelined implementation, you need to use more multipliers at once because you're not doing one convolution and then reusing the multipliers. You're using all of the multiplications at once. So for example, while in the non-pipeline decimation factor, you're doing roughly 15 multiplications per cycle. That's 15. Yeah, you're doing more like 21 per cycle in the pipelined implementation. And another thing is that rather than doing 32 additions in this case per cycle, you're doing 47 in this one. So you're doing a lot more operations at once, which is why the logic increases, but it's worth it for the execution time. And you want to handle that? Yeah.
Why do you have 105%?
Well, that's just what it's synthesized to. There's 20 multipliers on the FPGA we use, and in this design we use 21. Now, if we didn't really worry about that because our target device is not necessarily the Spartan, but if we were to target it towards the Spartan, we could implement one of our multipliers through lookup tables, which would increase this resource column. But this is the second least used. So if we wanted to make it fit, we could just implement our multipliers as lookup tables rather than using the core multipliers. So,
okay,
yeah.
so you're not using really a multiplier, you're using like a lookup table plus 20 multiplier, something like that.
If we were to put it onto the board, that would be the case, yes.
Okay.
But the goal is to use as many multipliers as possible because they're dedicated. And if you're not using them for that case, they just go unused. And so our future work is we really want to publish. We think there's a high potential because it's a very young field and this hasn't been done before. And to do that, we're going to have to keep in contact with Dr. Halampides and Arjun. And also, to facilitate larger images, we want to utilize DRAM. And not only does that facilitate larger images, but it also gives us a higher bandwidth on our reads. Because most DRAM can read 24 bits per cycle. It might actually, I think it's 32, which would allow 4 bytes per cycle as opposed to reading 1 byte per cycle. So we could exploit that to make our design even better. And any questions?
Yeah.
Yes.
One quick question. When you say you try to identify maybe a proper conference to publish the work, do you see any, what might be the key contributions that in your mind for along this study? And emphasis on the image processing techniques, steerable filter, or the implementation of FPGA, or combination of these?
Well, there's 2 main things. Most of them involve how we handle the steerability and the angles involved in that. For our non-pipelined implementation, the fact that we read in a diagonal way, that's somewhat novel, and it's also, it saves a lot of reads. And for our pipelined implementation in general is very novel. We haven't found anything like it so far. And it definitely exploits the parallelizability of FPGAs and shows how viable they are for image processing. So.
Okay, and in what you call that pipeline implementation, is it limited to steerable filter or maybe convolution, or maybe it can be explored to maybe some other type of image processing techniques?
Basically, any sort of image processing that involves multiple operations that are feeding each other, it could be used.
I don't know if you understand very well, but you can use, you said that you can use either multipliers or lookup tables. So what's the trade-off between using multipliers or lookup tables?
Well, basically on an FPGA, or at least the one we use, we have 20 multipliers and 20 BRAMs. And the BRAMs can store data and can be read and write, and multipliers can perform multiplication operations. They're basically blocks of logic specifically optimized and allocated for that purpose. So if we don't use our multipliers for multiplication, but we use, like let's say we're using 5 multipliers and then we implement another 5 multiplications as lookup tables, then the other 15 multipliers go unused, but we're cutting into our lookup tables available on the board. So there's really no reason not to use multipliers when you're using multiplication operations until you run out of them. In that case, it would be you'd have to move to multipliers or lookup tables. So it's just a matter of efficiently using resources, because lookup tables can be used for more than just multiplication, but multipliers can only be used for multiplication.
What is the memory of the lookup tables?
The memory of the lookup table?
Yeah, how many bits can you store it?
I'm not entirely sure. I think they're basically 2-input multiplexers is basically how they work. So I think each one is about a 1-bit, 2-bit operation.
You said that with the pipeline, you use more utilities on the board, correct?
Yes.
So compared to non-pipeline to pipeline, which one would be better? So it's sort of like a trade-off. You trade off time versus resources.
Yeah. Well, the pipeline implementation is preferable because there's no reason not to use all of the resources you have available. So assuming you were in a situation where you couldn't fit, you're using images so large that you couldn't store them. Well, it wouldn't be this. It would be the size of the image combined with the size of the mask. It's so large that you can't store it on the FPGA to do the pipeline implementation. Then in that case, it would be preferable to do a non-pipeline because the non-pipeline doesn't use temporary memory. Well, it doesn't use lookup table and slice-based memory. It would use BRAMs, or you could also use DRAM, which has a lot larger available size. So the only reason you wouldn't want to use the pipeline is if you're dealing with images or masks that are too large for your target device.
Yeah, and just in general, you use this like a dedicated logic unit anyway, so it's only purpose anyway, so you might as well just use it.
Yeah.
And also, with the decimation factor in pipelining, did that like have really bad? How did that affect your usage?
Well, it increased the usage and it increased the time because of the increase of zero pad.
Okay.
Slightly. It wasn't very significant, but it was definitely like the amount of blur that we gained for the amount of resources we gave. I'd say it's worth it. What we wanted to do was have a sigma equals 3 image to compare the decimation factor to, and we're definitely going to look into that because Harlan Beatty's his decimation factor paper was for a C and MATLAB implementation. So it hasn't been done on FPGAs yet, so we're still looking at the implications of using it on an FPGA versus a desktop.
Yeah, we really want to sit down and talk with Dr. Harlan Beatties about the decimation factor on FPGAs, or more uses of the decimation factor, and even extend the pipeline to have filters in multiple directions, which, I mean, that's the point of like an isotropic filter.
Yeah.
But really, we just wanted to show throughout this REU that we could apply a serial filter, not that we need to apply a full directional filter, because it's no more technique, it's just more Right.
Yeah, because essentially, once we do the horizontal and vertical convolution, we can, what we do is the horizontal, vertical, and then we do the 45-degree diagonal. But at that stage where the diagonal is being done, we could theoretically add a 15-degree, a 90, a 0-degree, whatever.
So it's like a proof of concept in a
Yeah,
sense.
because we could add all those in and at that stage, and they would all execute at the same time. So we could add as many filters as we want to create the full isotropic effect, and it wouldn't affect our time. It would only affect our resources. So
And definitely we designed this for a very low-level FPGA. I mean, the Spartan doesn't have a lot to it. It doesn't have a DRAM slot ability.
Okay.
yeah, so the Vertex boards, for example, have a lot more multipliers, a lot more slices. They're just they could definitely do bigger images and do more filtering. So,
Put a lot more on a small package and then take it to a bigger package and be able to still use the same idea, optimization
Yeah.
techniques.
Any other questions?
Thank you very much.
Whole OneNote thing.